Hi and welcome back to another automation video with the Siemens S7-1200 and factory I/O. In this video we continue from where we left off in the previous video where we modified a proportional controller to include integration. However, we left the testing of that PI controller for this video, so let's get started. Welcome back. Now this is where we were at the end of the last video. I've now uploaded the program to the PLC and we are ready to run. If you can remember, I said that I would start the testing by increasing the time constant t to see what effect this had on the controller. So we are starting at 0.1 seconds, which is 100 milliseconds. Then we will increase it in stages to 200, 600, 1 second and 1.7 seconds. I also said I would start Ki at 0.3, but really we need it bigger as we calculated in the previous video, closer to 3.5. Although, as we will see later in the video, the value of 2 or just under works quite well. Okay, let's accept the values and see what happens. At this stage we are only filling the tank and not adding any disturbance by opening the drain valve. The tank starts to fill and I'm going to freeze frame the system when the level in the tank reaches set point value of approximately 199.5. so that we can view the fill valve temp and the total error values. Okay, we've framed the screen as near to the set point value of 199.5 as we can, and PV real value is showing 200.3368. At this point, fill valve temp is reading approximately 29.38 and we have a total error of approximately 996. However, let's continue. So let's undo the freeze frame as the fill valve is still open and the tank is still filling. And we can see the fill valve starts to close as fill valve temp gets close to 0. By this time the tank's PV real value is approximately 249.6 and therefore we have overshot the set point by approximately 50 centimeters. This is often referred to as integral windup, and if we just wait for a while you will see the total error reducing. This is because the scaled error is now negative as we have overshot the set point, and this value is added to the sum of the previous errors to equal the total error. Then at the end of the interrupt scan, because sum of previous errors is equal to the total error, next time around when the interrupt runs again, the total error reduces again, and so on. In fact, if there is no disturbance, this value will keep reducing, and more importantly, so too will the fill valve temp value. I'll show you later in the video what effect this has on the ability of the controller to maintain the set point when a disturbance occurs, and why we need to stop integrating when we reach the set point to prevent this from happening. Right, let's stop the PLC and factory I/O. And let's change the time constant t for the interrupt to 0.2. To do that, let's open the properties of the cyclic interrupt and change it to 200 milliseconds and select OK. Then change the value for t in the watch table to 0.2 because the watch table is in seconds. Now we need to download the program to the PLC to overwrite the current cyclic interrupt. great. Now let's run the PLC and place factory I/O into play mode. Okay, now we can accept the modified values to start the system, and let's see what happens. Again, I will also freeze frame the system when we get to the set point to view the fill valve temp and total error values. Okay, we've freeze framed the screen again. This time the nearest we can get to the set point is 200.2684, as shown in PV Real. At this point, fill valve temp is reading approximately 30.19, but this time we have a total error of 499. This is because we are sampling half as much as before, every 200 milliseconds instead of every 100 milliseconds, which means the total error is calculated less frequently and comes to approximately half of the value it was previously, which was 989 when T was set to 100 milliseconds. Again, let's continue by undoing the freeze frame, as the fill valve is still open and the tank is still filling, and again we see the fill valve starts to close as fill valve temp gets close to 0. However, this time the tank's PV Real value is just over 250 instead of 249.6, as it was when T was 100 milliseconds, a slightly bigger overshoot of the set point. Again, we see the total error reducing on every scan of the interrupt because the scaled error is now negative as we've gone past our set point level, and the fill valve temp value continues to reduce at a steady pace of about 1 every 0.65 seconds. Now for the other values of T, rather than go through changing the cyclic interrupt and T and uploading it, I will edit these changes out from the video to save some time. After all, it's the result we want to view, and I'm sure we know the method behind it now. I will also speed up the footage by approximately 4 times to get the values we want slightly quicker. Right, this time the setting for T is 600 milliseconds, so let's accept the values and see what happens. Okay, the water level is now approximately 200 centimeters, and I'll freeze frame. The fill valve temp is approximately 30.58, and the total error is about 167.54, approximately 1/6 of what it was when T was equal to 100 milliseconds, which seems about right, as we are running the interrupt to calculate the total error 6 times less frequently. This time when the fill valve closes, we have PV Real equal to approximately 251.6, which is an even bigger set point overshoot, and notice the fill valve temp is going down by the value of 1 approximately every 0.55 seconds, so a little faster than before. Right, this time let's run the program with the value for T set to 1 second. Let's accept the values and see what happens. Okay, the water level is now approximately 200, and I'll freeze frame again. The fill valve temp is approximately 32.10, and the total error is approximately 102. About 1/10 of what it was when T was equal to 100 milliseconds. Let's continue, and when the fill valve closes, we have PV Real equal to approximately 254, an even bigger set point overshoot, and this time the fill valve temp is going down by the value of 1 approximately every 0.5 seconds. So again a little faster than before. Right, this is the last test for changing the value of T with a Ki value of 0.3. So I'm changing T to 1.7, which is 1700 milliseconds. So let's accept the values to run the program, and the tank starts to fill. Okay, the water level is now approximately 200 centimeters, and at the freeze frame, the fill valve temp is 36.38, and the total error is approximately 61.30. When the valve closes, we have PV real equal to 256.66, an even bigger set point overshoot. Now we could analyze all the results we've seen by plotting a graph, but essentially the three things to note are: 1, the overshoot increases slightly by increasing the value of T. 2, the total error reduces proportionately as we increase T with the values we've chosen. And 3, the bigger the negative error, the faster fill valve temp reduces when there is no disturbance. Other than these points, there's not really much else to conclude from this at present until we start increasing Ki, which we'll do shortly. However, it's worth me mentioning I decided to keep Ki quite small at this stage so that we could see the effects of increasing T alone had on the system. If I'd increased Ki to say 0.8 and carried out the same tests, we would have seen not only an increased overshoot, but the tank would have overflowed and we wouldn't have been able to note the actual water levels. Anyway, we'll see this increased overshoot shortly when we increase Ki. Now, as I mentioned earlier, the important thing to notice is the fill valve temp's negative value gets bigger over time. And while I've been talking, you may have spotted this actually happening. I've let the system continue running, and the values for total error and fill valve temp are becoming large negative values. This is because the integral part of the controller is still at work and is summing up the total of all the previous errors. As also mentioned earlier, this is what is known as integral windup, or should I say in this instance integral wind down. I don't actually think there's a term for that, but I'll use it anyway. Now, if the tank is filled and left for a while overnight, for example, this value could be huge, and the purpose of the controller is to try and maintain the set point level should water be drained from the tank. So if we drain some of the water from the tank, we would hope the controller would react and start to refill the tank when the water level goes below the set point value. So let's introduce a disturbance by draining the tank now, and let's see what happens. I'll just wait for the fill valve temp to decrease a bit further first. Approximately -115 will do. Okay, now let's start draining the water. And the water level is now going below the set point of approximately 200. But as we can see, the controller is not allowing the fill valve to open to replace the water being drained from the tank. So why is this? Well, until fill valve temp increases in value and becomes greater than 0, the fill valve will not open. And we can see this happening in a moment. Okay, we are starting to fill. then if I stop draining, we see the level go down again before the fill valve reopens. I think we can all agree this is not working very well. Okay, let's stop factory I/O and the PLC and consider what to do next. So essentially we have two problems that we have to solve. Firstly, we need to minimize the overshoot when we are filling the tank. And secondly, we need to stop the fill valve temp value reducing in size when we've reached the set point value. But before we try and solve these two problems, let's see the effect of increasing Ki has on the system in the next test. Now for this test, I'm going to put the value of T back down to 200 milliseconds, as 1700 milliseconds is rather a long time between sampling, even for a slow water tank like this one. And I feel 200 milliseconds is the best compromise for the PLC workload and response time for the system to get accurate results. I'll then set Ki to 0.6. We'll then upload the code to the PLC, then run the PLC and put factory I/O back into play mode. Then we can accept the new values in the watch table to get the system running again. Okay, let's see what happens this time. The tank starts to fill, and let's see how high it fills, even though we are only using a time constant of 200 milliseconds. Here we go. So look what's happening now. We have a bigger overshoot of approximately 88 centimeters. So we can see increasing Ki has a greater effect on the overshoot than T does for the values we've chosen. So if I'd increased Ki much more, the tank would have overflowed. However, the important thing to notice is the fill valve temp value decreasing at an even faster rate than before. And this is because we have a larger overshoot, and therefore the scaled error is a large negative value. This value makes up the total error on every scan of the interrupt and keeps accumulating in size negatively. So I'm just going to leave the system alone for a while and watch this value increase, or should I say decrease, with time. I'll speed up the footage a little for a while, then return back to real time. Okay, about 2 minutes has passed and fill valve temp is now approximately minus 200. So let's start draining the tank and see what happens. Wow, this time we get an even lower water level value of approximately 37 centimeters before the fill valve begins to open and start to refill the tank. So if we had left the system for an even longer period before starting to drain the water from the tank, then fill valve temp would have been a much bigger negative value, and we would have run out of water in the tank for a long period of time before it would have started to refill. I'm sure we all agree that in some circumstances this could be dangerous. For example, if this water tank was being used to cool down a nuclear power plant, who knows what would have happened. Not saying something this crude would be used for that purpose, but I think you understand how serious something like this could be. Right, let's make a slight change to the code to prevent this situation happening. I'll just scroll down in the code and you'll see that there are 3 lines that are commented out. Firstly, I'm just going to change the value of 20 to 0, then uncomment the lines of code. So what we are doing here is essentially checking for the water level to be greater than the set point value. And when this happens, because we get a negative error, we need to clamp or in effect stop integrating so that the fill valve temp value doesn't continue to decrease in size. Now this will bring up one additional problem, but we will come to that in a moment. So let's upload the new code and run the program. And I think with just this small change in the code, you will be quite surprised at the results. Now I've kept the values of T and Ki the same so that we can see the difference. So here we go. Okay, we are getting close to the set point value, and as soon as the scaled error, or the error for that matter, become negative, then the fill valve closes and prevents a large overshoot. Now let's just wait while the water level settles and see what happens to the error value and the fill valve temp value. As can be seen, they actually stop completely and there is no further accumulation of the error. Now let's drain some of the water and see what happens. As soon as we start to drain, the scaled error begins to increase, and so too does the fill valve temp. And it doesn't take long after the water level goes below the set point value for the fill valve temp to be greater than 0, and therefore the controller then allows the fill valve to open and refill the tank towards the set point, albeit very slowly because Ki, the gain multiplier, is quite small. Now I know we haven't reached the set point yet, but I'm going to turn off draining and see what happens. The fill valve starts to close and we only get a small overshoot. The overshoot is now smaller than when we were filling the tank. And the good news is this will always be the case during operation. However, as I said, the fill valve closes abruptly when the water level reaches the set point when filling the tank. And this is one thing we need to avoid, as it can reduce the life of the fill valve considerably. So let's make a small change in the code to prevent the fill valve closing so abruptly. Okay, I've just edited the code by making some of previous errors equal to 20 instead of 0. You could make this figure slightly bigger, but I'm happy with 20 and you will see why shortly. Okay, we'll accept the values in the watch table to start the system. Now let's wait and watch what happens when we get to the set point value. As we can see, the valve still closes a little abruptly, but doesn't go down to 0 straight away. And as you will see, when we increase Ki and the water tank is in operation, the action of closing the fill valve will be much smoother. Okay, let's wait for the water level to settle and see the errors and fill valve temp values settle. Great, that's working fine. Now I'm going to add a disturbance by draining the tank and calculate how long it takes for the set point to be reached while draining. let's also note how long it takes for the water level to stop reducing once it is below the set point value. It took approximately 4 seconds for the water level to stop reducing. So let's make a note of that. At this point you could have a coffee because it's going to take quite a while to reach the set point while Ki is so small. I'll speed up the playback a little to save time. I think we can safely say we are pretty much at the set point now, and this would be acceptable. Although we haven't quite got there in numbers terms yet, so let's just keep watching. The good news is PV Real has reached the set point of 199.5 centimeters and is holding rather well. Although, as I said, it does seem to take quite a while for the set point to be reached, and I would like to get there a little quicker. Right, let's see what happens when we remove the disturbance. The fill valve then closes a little more smoothly than it did before, and we only have a small overshoot. Now, if you do some research on the internet, you'll find that the speed for the water level in a tank to reach the set point when a disturbance is applied should be approximately 6 times the amount of time it takes for the water level to stop reducing below the set point. So in our case, it took approximately 4 seconds for the water to stop reducing, and therefore as a guide we would be looking for around another 24 seconds for the water level to return to the set point. But this timing will change when we choose a better Ki value, although the ratio of 6:1 would remain. We'll look at this shortly, but it should be stressed that this is only a guide should you be wondering if it's taking too long for the controller to react. Okay, as this is working well, albeit a little slowly, when refilling after the water level is below the set point, let's now increase Ki to the value we worked out in the previous video of 3.5 when using the Ziegler-Nichols method. And let's run the system and watch what happens to the fill valve when we reach the set point value. Here we go. It closes smoothly and we get a little overshoot. Now let's wait while the water level settles. Now let's add a disturbance and see how long the system takes to get back to the set point value. Well, as Ki is now quite big, we never get below the set point, and the controller tries to stabilize the system to a value of approximately 210. So what I'm going to do is reduce the value of Ki to 2 and see if we have a satisfactory response. So let's type in 2 and accept the watch table values again. And as you can see, the tank settles to roughly the set point. I'll just let the system run for a while. I'm going to reduce the value of Ki to 1.8 and see what happens. We can see the water level returns to the set point level smoothly and a lot quicker than it did when the Ki value was 0.6. Right, let's stop the disturbance and see what happens. The fill valve closes smoothly once the water level goes past the set point, and we get a small overshoot. Now, I'm quite happy with the way the controller is working. However, if you require to change the set point value during operation, then you really should recalculate the variables again for Kp, Ki and T using the Ziegler-Nichols method. You could also modify the code to include an if statement to select the appropriate values for these variables based on the value required for the set point. Well, that's all for this video. As I said in the previous videos, I don't think a PID controller is needed for this tank setup. However, for completeness, I will include the differential part in a future video, so that you at least have an explanation of the code for future applications. Now, there is one thing I should mention before we sign off, and that is we should limit the drain valve value to approximately 80% of the fill valve operating value. Otherwise, the tank could empty faster than it can be filled. Okay, until next time, hope you found this video informative. Thanks for watching. If you've enjoyed the video, please give it the thumbs up, and if you would like to learn more, then please click the subscribe button and the bell so you'll be informed as soon as a new video is uploaded. Please see the links in the description should you wish to get a free 30-day license for Factory IO, and also check out my Patreon account, and I'll see you in the next video. Now we've reached the set point and I'm going to close the drain valve. So bye for now.